Hello everyone, this is the challenge question walkthrough for Edexcel's Applied Year 1 textbook, and this is the last part in the mechanics section, and we're going to be going through all of the challenge questions in review exercise 2. Okay, our first question. A tram starts from rest at station A and accelerates uniformly for t1 seconds, covering a distance of 1,750 meters. It then travels at a constant speed v meters per second for t2 seconds, covering a distance of 17,500 meters. The tram then decelerates for t3 seconds and comes to rest at station B. Given that the total time for the journey is 7 minutes and 3t1 is equal to 4t3, find t1, t2 and t3 and the distance between station A and station B. So if we draw a velocity time graph for this here, so we have velocity going along this axis and time going along this one. So the velocity will be in meters per second and the time in seconds. So we have constant acceleration for the first part. So that will look something like this. So the gradient of the velocity curve is constant. Then we'll have that the tram is traveling at a constant speed for t seconds. And this constant speed is v meters per second. So this here is v. And then finally a deceleration for t3 seconds as it comes back to rest at station B. So we can split this graph into 3 sections, and we are given some extra information in the question that for the first portion of the graph we cover 1,750 meters, so that's the area under the curve. Here we cover 17,500 meters, and we also know that this portion of the graph takes t1 seconds, this takes t2 seconds, and the final part takes t3 seconds. Okay, and we're given some information about t1, t2 and t3. So we're told that the total time for the journey is 7 minutes. So we know that t1 plus t2 plus t3 is equal to 7 times 60, so that's 420 seconds. And we also know that 3t1 is equal to 4t3. Now we can use the distances that we're given to find another equation in t1, t2 and t3. And once we have a third equation, we can solve them simultaneously. So for this first area here, we have that 1,750 is equal to a half base times height, so that's t1 times v. And for the second area here, we have that 17,500 is equal to t2 times v. And if we call this equation 1 and our red equation equation 2, doing equation 1 divided by equation 2, on the left hand side we will get 17,500 divided by 1,750, so that's just 10. And on the right hand side we'll have t2v divided by a half t1v, and so the v's will cancel and we're left with t2 over half t1. Multiplying both sides by half t1, we get 5t1 is equal to t2, and that is the third equation we need. So I think the easiest way to solve these 3 simultaneous equations here is to rearrange this to get t3 in terms of t1, so that would be 3/4 t1. So we can substitute this equation here and this equation here into our top one, so we get an equation just t1. So we have that t1 plus 5t1 plus 3/4 t1 is equal to 420. And collecting the terms on the left hand side, we will have 27 over 4 t1 is equal to 420, and so t1 is equal to 420 times 4 over 27, and that gives us 560 over 9. And now using our other 2 equations to find t2 and t3, t2 is equal to 5t1, so 560 over 9 times 5, we get 2,800 over 9. And for t3, we have t3 is equal to 3/4 t1, so 3/4 times 560 over 9, we get 140 over 3. And we're also asked to find the distance between station A and station B. So we need to find this distance here as well. And so the area of this triangle is equal to a half times base, so that's T3, times height, that's V. So we need to find the value of V. So we can use that using either the blue or red equations, but the blue one is simpler, so I'll just use that. We know that T2 is equal to 2,800 over 9, so we have that V is equal to 17,500 over 2,800 over 9. And put that into a calculator, you get 225 over 4. Okay, and subbing in our values of T3 and V into the area over here, so that's a half times 225 over 4 times our T3, and that is 140 over 3. That gives us 2,625 over 2. So the total distance between station A and station B is equal to 1,750 plus 17,500 plus 2,625 over 2. And putting that into your calculator, you get 20,562.5 meters. And so that is equal to 20.6 kilometers to 3 significant figures. Okay, and our final question, question 2. In this question, we're told to use g equals 10 meters per second. One end of a light inextensible string is attached to a block A of mass 5 kilograms. The block A is held at rest on a rough horizontal table. The motion of the block is subject to a resistance of 2 newtons. The string lies parallel to the table and passes over a smooth light pulley which is fixed at the top of the table. The other end of the string is attached to a light scale pan which carries 2 blocks B and C, with block B on top of the block C as shown. The mass of the block B is 5 kilograms and the mass of the block C is 10 kilograms. The scale pan hangs at rest and the system is released from rest. By modelling the blocks as particles, ignoring air resistance and assuming the motion is uninterrupted, find for part A the acceleration of the scale pan. Okay, so first of all, we can add in our forces to this diagram. So if we focus on A first, we'll have tension going this way towards the pulley, and we'll also have the resistive force going this way with magnitude 2 newtons. Now looking at the scale pan, we'll have tension going upwards back towards the pulley, and we'll also have the weight of the scale pan going downwards. We're told that the scale pan is light, and the masses of B and C are 5 and 10 kilograms. So the total mass of the scale pan is 15 kilograms, so its weight will be 15g acting downwards. So as usual, we're looking to use F equals ma on the particle A and also on the scale pan. So looking at A first, resolving to the right using F equals ma, we have that T minus 2 is equal to the mass of A, so that is 5 kilograms, times the acceleration. And doing the same for the scale pan, if we look at it as a whole, resolving downwards, we have that F is equal to ma again. So we have 15g minus T is equal to 15a. And now if we add these two equations together, so let's label this one 1 and this one 2, adding these equations together, we have 15g minus 2 is equal to 20a. So we see that the acceleration is equal to 15g minus 2 over 20, and using g equals 10 as we're told to in the question, we have 150 minus 2 over 20, and that gives us 7.4 meters per second. And as the string is inextensible, we know that the acceleration will be constant throughout the entire system. So the acceleration is 7.4 going in this direction, and also 7.4 going in this direction. Okay, for part B, we're asked to find the tension in the string. So we can use the first equation. We have that T is equal to 5a plus 2. So 5 times 7.4 plus 2, we get 39 newtons. So for part C, we're asked to find the magnitude of the force exerted on block B by block C. So if we look at the blocks B and C, if I draw them out again here, what's actually going on is that if we focus on B only, then what's actually going on is B experiences its own weight, so that will be 5g, and also a normal reaction force from C, and we'll call that RC. And those are the forces that B is experiencing. And we know that the acceleration is 7.4 going downwards. So we can use F equals ma on just the block B. So if we resolve downwards, we have that F, so that's 5g minus RC is equal to the mass 5 times the acceleration, 7.4. Okay, and for part D, we're asked to find the magnitude of the force exerted on the pulley by the string. So if we think about what's actually going on with the pulley in terms of forces, we have tension acting in this direction from the block A, and also tension acting in this direction here. So if we look at the forces acting on the pulley, there's tension acting this way and tension acting up this way. And we can resolve these forces if we draw in this line here. We know that these two angles must be 45 degrees, as the two tension forces are acting perpendicular to each other. And we can use these two right triangles here to resolve perpendicular and parallel, like so. And for the other tension force, we'll have the forces like this. And you can see that these two forces here and here will cancel each other out, as they're equal forces in opposite directions. But these two forces here are acting in the same direction, and that is what the pulley will experience, a force coming out like this, and let's call that force F. And to find that, we just need to find what the magnitude of these forces here are, and we can use that using trig. So if we draw out one of these triangles, we have the right angle here and 45 degrees here. We can see that cos of 45 degrees is going to equal this force here. Let's call that P. So cos of 45 degrees is equal to adjacent, so that's P over T. And therefore we get that P is equal to T cos 45 degrees. And we have two lots of those forces here, the one in red and the one in blue. So we have that the force F here, because the pulley stays still, the forces must be balanced. So we have F is equal to the two forces here, and that is equal to 2T cos 45 degrees. And from earlier, we know that T equals 39 newtons. So we have 2 times 39 times cos 45. That equals 39 root 2, or 55 newtons, to two significant figures. And for the last part, part E, states how in your calculations you have used the information that the string is inextensible. So we use that in parts A and B to assume that the tension is constant throughout the string, and also to assume the acceleration of the block A, and the scale pan is the same. And that is the end of the mechanics section for Edexcel's Applied Year 2 textbook.